right, fam. This is my 5th time trying to record this part of this lesson. The last well, maybe not obviously, but I'm in a different outfit because I was able to record part 1 yesterday, but then 20 minutes into this part of the lesson, the program said that the file was corrupted, and it was like 5 p.m. and I rage quit. So I'm hoping that these lesson videos are continuous, but it's better when I do them one after the other, so there may be some things that I leave out or assume that I did, but I didn't do. So I will do the best that I can, and I apologize that this part of this lesson has taken me forever to get to you guys. I think I have all the issues figured out now, so fingers crossed we're good from here on out. So as far as I remember, the last thing that we did in this lesson was talk about the conditions that we check for making confidence intervals for a mean. And it's similar to what we checked in the last unit for sampling distributions, and it's similar to what we check for confidence intervals for a proportion. But there is one part of it that is time consuming. I wouldn't necessarily say that it's complicated. I would say that it's very time consuming. And that is related to this bottom part of our notes on page 618. So it has to do with our normal or large counts condition. If our sample size is greater than or equal to 30, everything's good and the process is relatively short and hopefully easy. If our sample size is less than 30, then that's where we really have to spend time verifying that we can do a T procedure. How do we verify that? We have to look at a graph of our sample data. So we have to graph our sample data. If our sample data is strongly skewed, then that means that the population is probably strongly skewed. If it has outliers, that means that the population probably has outliers. And if the population looks like that, then we can't use a T procedure. So where does the time-consuming part come in? Well, we have to make the graphs. If we need to analyze a graph of the sample data, most of the time they are expecting us to graph the sample data, and that just makes the process a little bit longer than any of us would probably like. So last time we went over these conditions, and then luckily we got one hopefully easy example. I say hopefully because I'm hoping that you find this process pretty easy. I went pretty quickly through this problem, mostly because if I'm being real, I'm tired of this lesson, so I'm trying to get through it as fast as possible. But I'm feeling in a little bit better spirits today, so I think this part of the lesson will go a little bit better. So went over all the conditions, did one manageable problem. So now we are getting into the tough stuff. So I'm going to read you the setup for this problem, but while I do that, I would like for you to get out your calculator and enter this data set into one of your lists. So to do that, you need to hit your Stat button. You need to choose option 1, which is Edit. And then make sure that if you need to clear out a list, you hit Clear and not Delete. So to enter this, sorry, I just need to grab my other calculator. We're going to hit Stat, Edit, and then you can see I've already put mine in list 1. Okay, so you're entering in these values while I read the prompt, and if you're not done by the time I'm done, just pause the video and finish up. A manufacturer of high-resolution video terminals must control the tension on the mesh of fine wires that lie behind the surface of the viewing screen. Too much tension will tear the mesh, and too little will allow wrinkles. The tension is measured by an electrical device with output readings in millivolts. Some variation is inherent to the production process, so that's why in the 20 screens that you see below, the readings are different. It's okay for the readings for each screen to be a little bit different. So they look at 20 screens from a single day's production, and they want us to construct a 95% confidence interval for the mean mu tension of all the screens produced on this day. So to fill in the what portion of our response, we are estimating mu, which is, and then we're going to copy down what I have highlighted here, the mean tension of all screens produced on this day. How are we going to do this? Well, we are going to do a one sample T interval for mu. And then I typically like to highlight this just to reiterate to you guys that it is essential that you write down what procedure or method we're using. I check my conditions based off of the formula. So I know that anytime they give me the data set, I am going to have to calculate the statistics that we're interested in. And I was reminded to say that because the first element of my formula is our X bar. But we don't know our X bar. In this previous problem, we were given the statistics we needed, 110 and 27. In this problem, I have to find those statistics by using my calculator. So to do this, I'm going to put the directions over here. You can put these directions wherever you want, like maybe they make more sense to you here. In fact, maybe I'll just put mine there. We have to hit the Stat button, arrow over to Calc, and we need to choose option 1, which is one variable stats. When you plug this in, this is going to calculate for you your X bar. Sorry, I'm just getting a pen. You know, that takes me 10 years sometimes. It's going to give us our X bar and our SX. So mine is in list 1. I'm going to do Stat, arrow over to Calc, choose option 1. To change this to list 1, I'm going to hit blue button, the number 1. I'm going to enter all the way through. And here is the data that I need. So my average screen tension is 306.32 millivolts. And my standard deviation, S, is 36.21 millivolts. And then I would just like to reiterate my thought process on this. So I listed the procedure that I was going to use, and then I use this formula as a reminder of the conditions that I need to check. When I saw this X bar, that reminded me I actually have to calculate the statistics that I want, and that is the X bar and the S sub X. This also is my reminder to make sure that this sample was random. And it was right here. It says a random sample was taken. I usually don't write that down because it's not required to earn full credit for this. It just, we just have to make sure that our sample is random so we can make inference about the population. Next up, we have to decide if a T critical procedure is appropriate. And how we do that is deciding if we have large counts. Large counts would be n is greater than or equal to 30. Unfortunately, in this problem, n is 20. That means that we need to check to see if the data came from a normal population. So if I flip back to my conditions, if I have large counts, everything's fine. If I do not have large counts, I need to verify that the population is normal. To do that, you have to graph the sample data. And this is 3 graphs that you can use. The first one is a dot plot. This is the one we're most familiar with. This second one we learned in Unit 2, and this is your normal probability plot. If this plot has a linear pattern, then you can say that your data is approximately normal. If this has a linear pattern, you can say your data is approximately normal. Then this is a regular old box plot. Now, I've mentioned many times that the box plot is the one that I prefer for several reasons. One, I think that it's the easiest to graph. This one, you have to make your axes and plot all 20 points. This one, you have to sketch all 20 values. This one, you can use the 5-number summary. And that's what makes it a little bit quicker to graph. The other reason that I like this is because box plots truly show if you have outliers. And I mean outliers according to the 1.5 times IQR rule. If we're stating whether or not a distribution has outliers, we should really mathematically verify that that is the case. Well, if you check this in your calculator does the work for you, and it will show up, and by it I mean outliers will show up as points outside of your box plot. The last thing, or the last reason that I prefer to do the box plot as my graph to show that I can use a T procedure is because a lot of the time I have to calculate X bar and S, and to get my 5-number summary to make the box plot, it's all on this same screen. So I can pull my X bar, my S, and then I can also pull the 5-number summary. And if we compare these two things, we can see that they match. So for instance, our minimum is 233.5. That looks like 233.5. Quartile 1 is 275. That looks like it's about 275. Median 308. Quartile 3 is 337. And then last, our max is 375. So, several reasons why I prefer a box plot. Just to recap, if you have to graph your sample data, your options are a dot plot, a normal probability plot. You can do a box plot. You can also do a histogram, but I think that a histogram is for me personally, way too complicated to do under testing conditions. I already have test anxiety personally, so I personally need to use a method that is tried and true and easiest for me, and that is the box plot. So, that all being said, what we're looking for in this box plot is that it's roughly symmetric with no outliers. Because, remember, if our graph has strong skew or outliers, we can't use the data. This one, roughly symmetric with no outliers. So now we have to describe that here. We can use a t-distribution because the box plot of the sample data is roughly symmetric with no outliers. Pause if you need more time to write that. Why does this matter? So why does it matter if my sample data is roughly symmetric with no outliers? Well, the reason why is so we can say it is reasonable that this sample came from a normal population. Pause if you need to finish this one. Okay, you can see, hopefully, that I have written that last part in a different color pen. If you are a good memorizer and you are going for a 5 on your AP exam, you need to write this whole statement. The box plot of the sample data is roughly symmetric with no outliers, so it is reasonable that this sample came from a normal population. Because you need to show the understanding that you know you can only use a T procedure if the population is normal. And the reason why is because our sample size is less than 30. Now, I'm pretty sure that what I have in black is enough to earn you most of the credit, if not full credit. That being said, there were a lot of kids last year that were right on the borderline of a 2 to a 3, and I would hate for you to be moved to the 2 category and not earn your credit because you didn't want to have to write this down. While we're learning this, it's very cumbersome because you have to practice the procedure, and so you end up having to write this several times, and I know that that's unenjoyable. But it will pay out in the end on the test if you remember to do it, and that gets you one step closer to earning your college credit for this class. So, it's a double-edged sword. I know it's a lot to write, but it will go a long way in helping you get all the points you need to earn a passing score. Okay, we've been doing this problem for like 20 minutes now, and we're only like halfway done. So, I calculated my statistics. I determined that I can use a T procedure, so now I'm going to find my T critical. My degrees of freedom are 20 minus 1, which is 19. So if I look this up on my pink table, I go to 95% at a sample size of 19, and that gives me a critical value of 2.093. Last thing that we need to check is the 10% condition. N in this case is all screens produced on this day. Well, I have no idea how many screens they can produce in a day, so I definitely have to say, so it's reasonable that 20 is less than or equal to 1/10 N. In the last problem, I was sure. I was sure 66 was less than 1/10 of the population. In this one, I have no idea, so I'm just going to say it's reasonable to assume that they make at least 200 screens a day. So you are finally to the point where you can construct your confidence interval and you can write your conclusion statement. So you guys try that without me, pause, try it without me, and then come back and verify that your answers are correct and match mine. So I have a confidence interval of 289.4 millivolts to 323.3 millivolts. So hopefully what you have is exactly the same as what I have. Like exactly the same. Okay, so we have done an easier, quicker interval for mu. We've done one that was more time consuming, but I provided the graphs for you. So we were supposed to make these graphs on our own, but just to get through one problem where we actually use this process, I put the graphs in for you. So now, the last problem is the whole shebang. We got to do it all on our own. So you enter in these values into your calculator while I read you the prompt. If you need extra time, pause the video. Biologists are studying the healing of skin wounds measured... I didn't read that right. Biologists studying the healing of skin wounds measured the rate at which new cells closed a cut made in the skin of an anesthetized newt. So a newt is like a water lizard. Like if you Google it, he's like a lizard-looking thing. Below are the data from a random sample of 18 newts. These are measured in micrometers per hour. Calculate a 95% confidence interval for the mean mu healing rate for newts. So, two things to observe up front. One, my sample size is 18, which is less than 30. So, I'm going to need to make a graph. The other thing that I know is because they've given me the data set, I am also going to need to find the statistics required to make my confidence interval. Part number 1 is stating what exactly are we doing. So we are estimating the mean mu healing rate for newts. So I basically just copied what I highlighted in green. How are we going to do this? A one sample that doesn't require a hyphen. T interval for mu. And at this point, I am going to gather the statistics that I need, and I'm going to make my graph. So as soon as I say what method I'm using, I'm going to run my one variable stats and then make my graph. So I'm going to double check what list my data's in. So mine is in list 2. I'm going to go to Stat, arrow over to Calc, choose option 1, and I need to change this to list 2. So I'm going to do blue button, 2. Enter through, and I'm going to pull these numbers. So 25.6 with a bar. And my S sub x is 8.32. Now, I know that I'm going to need my 5-number summary because I always make a box plot. If you're going to make some other plot, then you need to pull the data that you need. So my minimum is 11. My quartile 1 is 22. Median is 26.5. Quartile 3 is 33. And my max is 40. I need to verify whether or not there are outliers, though. So I am going to have my calculator graph a box plot because that's going to be the easiest way for me to decide if there are outliers. I have to do this, I'll write the buttons right here underneath my 5-number summary. To graph, you hit your blue button, which is your second button, and your Y equals button. So, blue button, Y equals. I'm going to verify that I have only one plot on, and then I'm going to select the number of the plot that is on. So I'm just going to select number 1. This top right is a histogram, so if you wanted to graph a histogram, you would enter in on that. Make sure that you have the right list. Hit graph. Well, that doesn't look very good. So the key is to hit zoom stat, which is option 9. So zoom 9, and I could make a histogram of the data. This histogram does look roughly symmetric, and there doesn't appear to be any outliers. I personally like to know for sure whether or not there are outliers, which is why I choose the box plot. So I go back to my Y equals, and if I want the box plot, I'm going to choose the one that looks like it has outliers. Just going to hit enter, then I'm going to hit graph. The box plot is in my screen, luckily. I don't see any outliers. I don't see any outliers. I'm going to check the other box plot just real quick. You don't have to ever check 2. I just want to see what it looks like. Yeah, so it looks exactly the same. So I always just choose the one that looks like it has outliers. And I'm not looking at the graph so that I know how to graph it. I'm looking at the graph to see if there are outliers. So now that I've checked that, I'm going to do my box plot. So I'm going to draw my x-axis that represents the healing rate. My minimum is 11, so I'm going to start my axes at 10. My max is 40, so that's as high as I need to go. So I'm going to go by 5s until I get to 40. Ooh, that worked out nicely for me. And then I'm going to graph my 5-number summary. So I put a point at where 11 is. 22. It doesn't have to be perfect, it just has to be close. 26.5, 33, 40. Then I construct my box plot. So if you need more time, you're going to pause and take the time to finish up. Okay, now it's time to check conditions. I always use the formula to check conditions. Some of you guys like to go right in and write your numbers and check. It's up to you. I personally think this is a lot cleaner. X bar, was my sample random? Yes. My newts were a random sample. Can I use a t-distribution? Well, what I write here is going to be exactly the same, 100% the same as what I wrote here. So pause the video and copy this statement down. Use the t-distribution because the box plot of the sample data is roughly symmetric with no outliers, so it is reasonable that this sample came from a normal population. Now, please forgive me. I have done this lesson 10 times in the past 2 days. So I ain't going to write that down again. I'm not doing it. Love you though. You do it. I'm not doing it. Okay, you write down the whole shebang. And then let's use our, use this space to write down our degrees of freedom. Is 18 minus 1. So 17. And our T critical. I'm not going to find your T critical for you this time. You find your T critical. So we have a random sample. We are allowed to use T procedures because this box plot is roughly symmetric with no outliers, which means it's reasonable to assume that this data came from a normal population. Last up is our 10% condition. I don't feel like they make it very clear what N is. So for N, I'm saying that it's all available newts. I don't know how they get their newts. I don't know where they get their newts from, but the population is all newts that are available to them. So it is reasonable that 18 is less than or equal to 1/10 N. Hopefully, these biologists are going to the body of water that these newts live in, and there are 180, at least, newts in this body of water. I have no idea, though, so I'm just going to say it's reasonable to assume and get on with my life. So, the last portion is for you guys to construct your confidence interval and write your conclusion, which I would like for you to do on your own, because that's how you're going to get the most out of this. So pause the video, Famil. Pause the video. Try the problem. Come back when you're done. Please bless that you really paused the video. So, as you can see here, I did write all the stuff down for 5 times now. So this is my statement of why I can use the T distribution. My T critical was 2.110. my interval I set up like this. Now, I realize that I probably should have used 25.7 here. So if you use 25.7, because notice up here, it's 25.6 bar, which means I really should have rounded to 25.7. So if your value is slightly off of mine, we're totally Gucci. Okay, that's fine. My statement is we are 95% confident that the interval from 21.46 micrometers per hour to 29.74 micrometers per hour captures the true mu healing rate for newts. The abbreviation for micrometers is looks like this. Mine looks a little bit too much like mu, but it's really this. Or you can just write out the words micrometers. Okay, so brief recap, then you're done. What have we done in this lesson? Well, we talked about the conditions that we need to check for constructing intervals for a mean, and unfortunately there's a little hiccup when it comes to large counts. If your sample size is bigger than or equal to 30, everything's gravy and life is good. If it's less than 30, then we got to graph some things and use our calculator, and it takes a little more time. We did an example that's very straightforward with large counts that are met, so n is greater than or equal to 30. We did an example that included a little bit of help. I provided the graphs for you, and then you did the confidence interval. And then our last problem was the whole thing. And this is the kind of thing that you would expect on the AP exam, because you need to know 2 chapters to do this instead of just 1. You need to know how to find your statistics you're interested in. You need to know how to build the graph, and you need to know how to make the confidence interval. In fact, it's really 3 chapters, because you need to know how to graph your data, you need to know the basics of a sampling distribution, and you need to know confidence intervals. So they're addressing a lot of different ideas in this one problem, and that's what they like to do on the exam. Okay, you survived. I love you, Mooey. I hope that you have a great day, and I'll see you in the next one.